In today's lesson, we will be talking about limiting reagents. The other terms that are involved in the reaction are excess reagent, theoretical yield, and percentage yield. Let's define the term limiting reagent. If the quantities of the reactants are known, the reactant that is completely used up according to the balanced chemical equation is called the limiting reagent. So let's look at a problem. So here is a sample problem. When 16.3 grams of magnesium and 45.2 grams of oxygen react, how many grams of magnesium oxide will be formed? The reaction is between magnesium and oxygen to produce magnesium oxide. In this problem, we have to identify the limiting reagent and the excess reagent, then determine the amount of unreacted excess reagent that is available in the reaction mixture. These are the steps we can adopt. The first thing that we would need is a balanced equation. The balanced equation is 2 mg solid plus O2, giving you 2 MgO. Next, we will have to determine the molar masses of the reactants and products. Molar mass of magnesium oxide will be taken as 40 grams per mole based on the calculation represented. Molar mass of magnesium is 24 grams per mole. Molar mass of oxygen is 32 grams per mole. This is for diatomic oxygen. The next steps involve the fractions that we will be using based on dimensional analysis. So in this case, we are going to look at the relationship between 2 mg and MgO. We're not concerned about any other reactant at this time for this specific calculation. So we're going to see the relationship between magnesium solid and magnesium oxide. So we're going to see how we can convert this using dimensional analysis. The quantity we are starting with is 16.3 grams of magnesium, and we want to convert it into moles. So the conversion factor for mass to moles of magnesium is 1 mole of magnesium divided by 24.00 grams. Since we are given the mass of magnesium, in the second column, the conversion factor, the denominator should be mass or molar mass of magnesium, which is 24 grams. So converting the quantity magnesium in grams to magnesium in moles. So we will cancel out the common terms. So the result of this calculation, dividing 16.3 by 24, will give you the number of moles of magnesium. Next, we have to convert and determine how many moles of magnesium oxide will be formed when the quantity of magnesium taken will undergo complete combustion or oxidation. So that's the second step. So we're going to convert the moles of magnesium to moles of magnesium oxide. In order to use this, we will use the coefficients in the balanced equation. In this case, the values are 2 and 2. In the conversion factor, the denominator should have the moles of magnesium so that it cancels out with the numerator. So moles of magnesium on the reactant on the number of moles will cancel out with the moles in the conversion factor for identifying the number of moles of magnesium oxide. So what we have right now at this point will be the number of moles of magnesium oxide that is formed. The next step would be converting the magnesium oxide moles into grams. That's the next step. So magnesium oxide to grams can be converted by multiplying it by the conversion factor, the molar mass of magnesium oxide. Now we want to cancel out the moles of magnesium oxide with the denominator on the right side in the conversion factor, and therefore we should have 1 mole of magnesium oxide in the denominator, and in the numerator we have the molar mass of magnesium oxide, which is 40. Now if you cancel the units, we will get grams of magnesium oxide. So if you solve for the numbers or the fractions that are written here, you should get 27.17 grams of magnesium oxide. We can simplify it by writing it like this. So 16.3 divided by 24 times 1, because the ratio of 2 by 2 is 1, times the molar mass of magnesium oxide gives you 27.17 grams of magnesium. So we finish one part of the calculation, that is determining the amount of magnesium oxide that can be formed from 16.3 grams of magnesium. That's the first part. Again, we have to look at the amount of magnesium oxide that is produced when oxygen undergoes complete combustion. Okay, that's the next step. So now you're going to look at the relationship between oxygen and magnesium oxide. We are not interested in the amount of magnesium at this time. So we are going to look at the relationship. Now you will also notice that the number of moles of oxygen is 1 and the number of moles of magnesium oxide is 2. So the ratio is 1:2. So we will write a fraction just like in the previous case. So we will start with oxygen in this time. The quantity of oxygen given is 45.2 grams. And the first thing to do would be to convert 45.2 grams to moles. So you multiply it by a conversion factor. And in this case, the grams should be cancelled. So we will write the factor as 1 mole of O2 divided by 32 grams, which is the molar mass of oxygen molecules. So converting the quantity in grams to moles, mass of oxygen to moles of oxygen, we need to multiply 45.2 by 1/32. The next step would be converting the moles of oxygen you have to the corresponding amount of magnesium oxide that is formed in moles. So the conversion factor there, we're going to use the coefficients of the equation. For every mole of oxygen, you will get 2 moles of magnesium oxide. Since we already have the number of moles of oxygen, we want to convert that into the number of moles of magnesium oxide it is equivalent to. So we multiplied by 2 moles of magnesium oxide in the conversion factor and divided by 1 mole of oxygen so that the units moles get cancelled out from the previous term. So this is what happens. We are converting moles of oxygen to moles of magnesium oxide. We will cancel out the common terms, the units of moles of oxygen divided by moles of oxygen. So the number that we will get after the second conversion is moles of magnesium oxide. This leads us to the third step, which would be changing the moles of magnesium oxide to grams of magnesium oxide. We need to multiply it by a conversion unit. The unit is 1 mole of magnesium oxide. The mass is 40 grams. You write it such that the moles or 1 mole of magnesium oxide cancels out with the mole of magnesium oxide on the left so that the final unit will only contain grams. Moles of magnesium oxide to grams of magnesium oxide. That's the third conversion. Cancel out the terms that are common. Now the only unit that is remaining is grams. Therefore, if you solve using this fraction, you will get 113 grams of magnesium oxide. Or to simplify it, you'll find that you have changed the 45.2 grams of oxygen to the final product, which is expressed in grams, is magnesium oxide. Or we can say 45.2 divided by 32 times 2, because the ratio is 2:1, times 40 gives us 113.00 grams of magnesium oxide can be formed. So what we did right now is we took oxygen as the reagent that undergoes complete reaction. And if that were to happen, the amount of magnesium oxide that it should have formed is 113 grams. So we have two values that we calculated. We calculated the amount of magnesium oxide formed when 16.3 grams of magnesium underwent complete reaction. And we used the second number, that is 45.2 grams of oxygen, and we converted into magnesium oxide. Here we got 113 grams of magnesium oxide. So here we have a problem. The question says the quantities taken are very specific, 16.3 and 45.2. If one of the reactants is giving you a specific number and the second reactant is giving you a much different number, then we have a problem, which tells you that one of the reactants is not completely reacting, or one of the reactants is completely reacting. Both of these are true. So let's do a simple analysis. Based on the calculation that we just did, we know that 16.3 grams of magnesium will produce 27.17 grams of magnesium oxide, and 45.2 grams of oxygen will produce 113 grams of magnesium oxide, provided all of the reactants completely react. So if 16.3 grams of magnesium completely reacts, you will only get 27.17 grams. And if 45.2 grams of oxygen completely reacts, assuming that it has the right amount of magnesium, it should produce 113.00 grams. So if you are mixing 16.3 grams of magnesium and 45.2 grams of oxygen, you cannot have two different numbers. You will only have one number. So that would be 27.17 grams because oxygen is present in excess. So the limiting reagent is a reagent that is completely used up. In this case, it will be magnesium, which is 16.3 grams, and you will get 27.17 grams. And you will not get 113.00 grams of magnesium oxide because you do not have sufficient quantity of magnesium to react with all of the 45.2 grams of oxygen. So the reagent that is completely used up is magnesium, and so it is a limiting reactant, and oxygen is the excess reactant in this case. So that's how you determine the limiting reagent. You do separate calculations for each of the reactants. If there are 3 reactants, you'll have to do 3 separate calculations. The quantity that is least, that is producing the same substance in the product side, will determine which reactant is a limiting reagent. So in this case, it is magnesium. Excess reagent. If the amount in mass of products formed in a chemical reaction is determined by the limiting reagent, the amount of unreacted second reactant is called the excess reagent. So we found in the previous calculation, we would have got 113 grams of magnesium oxide because we have 45.2 grams of oxygen, which also told us that all of the oxygen was not reacting to give us the quantity that oxygen could have given. Since we only had 16.3 grams of magnesium, only a part of the oxygen was used up in the reaction. So we need to calculate excess reagent, which we did in the previous slide. Now we also want to calculate the amount of unreacted oxygen. That's what we're going to do. So now you can define excess reagent as the reagent that is present even after the reaction is complete. For the given reaction, we want to determine the amount of unreacted or excess oxygen. So the reaction in this case, we are only interested in the relationship between magnesium and oxygen. We're not looking at the amount of magnesium oxide formed. We want to find out the number of moles of the limiting reagent, which we already did. And then we want to find out what is the quantity of oxygen that is needed to completely react the limiting reagent. If you have the moles, we can also change it into grams and then find out how many grams have reacted and how many grams are still remaining unreacted. That's what we're going to do here. So if you write the fraction like we did earlier, so in this case, we are going to compare 16.3, which is magnesium, and change it into number of moles. So the quantity in grams is converted into moles. Then we convert the moles into the corresponding amount of oxygen that will be used up in moles, and then convert that back into grams. So we have cancelled the common terms on the left. Grams have been cancelled out. What we have is moles of magnesium. Now we're going to convert the moles into the moles of oxygen that is required. So you multiply it by 1 and divide it by 2 because we need to cancel out the common terms here of moles of magnesium and moles of magnesium. Therefore, the denominator coefficient in the balanced equation is 2. So that's what we have written in the denominator. In the numerator, we have the number of moles of oxygen. If there is no number, the number is taken as 1. And the final step would be converting the moles of oxygen to grams of oxygen. We need a conversion unit. And in this case, we will convert moles of oxygen to gram by multiplying it by the conversion unit. 1 mole is 32 grams. Since we need the moles unit to be cancelled out, it's going to be written as the denominator and multiplied by the molar mass. So now you're cancelling out the units of oxygen, which is moles of oxygen. The final unit that is remaining is only grams. And solving this equation or this fraction, you will get 10.87 grams of oxygen has been completely used up. And the final answer is expressed in grams. Let's rewrite it. 16.3 divided by 24, again divided by 2 times 32 is equals to 10.87 grams. This is the amount of oxygen that actually reacted with 16.3 grams of magnesium. So if you want to find out the amount of unreacted oxygen, you have to subtract this number from the amount of oxygen you started with. So we started with 45.2 grams of oxygen, 10.87 grams reacted with 16.3 grams of magnesium. So the amount of unreacted oxygen is equals to 45.2 grams minus 10.87, which is 34.33 grams. So that's how you determine the amount of unreacted excess reagent. Notice that every time we are doing a calculation, there is a relationship between two terms. It could be between two reactants, or it could be between one on the reactant side and one on the product side. Therefore, whichever quantity you take has to be multiplied by 3 fractions. The first one is conversion to moles. The second and third, again, conversion based on the equation. And the last term is actually converting the moles back to grams. Those are the common terms that you will see for every limiting reagent problem. So the variation in the type of problems that you can see are here. Theoretical yield, the amount in mass of products expected out of a balanced chemical reaction, is called theoretical yield. It depends on the limiting reactant in the reaction. So in this case, we determine the theoretical yield of magnesium when we took 16.3 grams. From the above calculation, we have showed that 16.3 grams of magnesium will produce 27.17 grams of magnesium oxide, and that is the theoretical yield. Now we have one more term, it's called actual yield. Actual yield is the amount of products obtained in a lab or industry when performing the chemical synthesis. In this case, we are preparing magnesium oxide from magnesium and oxygen. So if you took 16.3 grams, you would have obtained the quantity that we calculated. Normally, that's the value that we should have got. But when you perform an experiment, it's not possible all the time to get the same yield, the 100% yield that the equation tells us we should have. There are various reasons for it. It could be the purity of the reactants that we have. It could be the experimental conditions that we are meeting. All of these would have to be taken into account, and only then we will know whether the reaction is going to 100% yield. Most of the time, the yield obtained, the actual yield obtained for the reaction in a lab or an industry is less than 100. When this activity was performed in a lab with 16.3 grams of magnesium and excess of oxygen, the amount of magnesium oxide formed was 24.3. The amount obtained in this experiment is called the actual yield. In this case, the yield is less than the theoretical yield. One of the questions that you should ask yourself is it possible that the actual yield can be greater than 100%? So let's calculate the percentage yield for the given question. Percentage yield can be calculated using the equation actual yield times 100 divided by theoretical yield. So this is the equation that we'll use. So the quantitative amount in percent of product obtained in a chemical reaction depending on the actual yield and theoretical yield is what we refer to as the percentage yield. So let's use this equation and calculate the percentage yield for this reaction. The theoretical yield for this reaction is 27.17 grams. The actual yield was 24.3 grams. Percent yield is equals to actual yield divided by theoretical yield times 100. Substituting the numbers, we get the percentage yield to be 89.45%. If you have the percentage yield, you can also calculate percentage error. 100 minus percentage yield is equals to percent error. So in this case, 100 minus 89.45 is equals to 10.55%. That's it for now.